Okay, so let's start then. So we'll wrap up our discussion related to MOSFETs today. And while we are discussing MOSFETs, I'll use examples to illustrate some of the important concepts. And this is the results I will use from simulation. So this is the MOSFET structure, and some of the results that I'll show you pertains to this particular structure here. And you can see we have source and drain here, and the substrate is here. The doping in the substrate is uniform, 2 times 17. The thickness of the oxide is 10 nanometer. You can hardly see on this particular scale here because the substrate for the purpose of simulation has been kept as 1.5 micron. You know that the substrates are 300 or 400 micron thick, right? So even on this scale, you can hardly see the oxide because it's only 10 nanometer here. The work function of the gate here is 4.3 eV. For discussion for today's lecture, we'll take mostly a long channel MOSFET with a fairly long channel here, 5 micron. The width, because it's a two-dimensional simulator, so by default it keeps the width equal to 1 micron. But then for any other width, all you have to do is multiply it by that value here, right? So whatever is the width, if it's 10 micron, whatever you get, you multiply current by 10, you'll get that here. The channel mobility of electrons in the channel is right now being assumed to be constant, is 500 here, right? And so this is the structure of the MOSFET, and at various points I'll show you results obtained from simulation for this particular structure here. All right. The other thing that note that what typically happens is, you define when you make a MOSFET, you define that you want a channel length of 5 micron. So on the top of the substrate, you put a silicon dioxide and you put polysilicon and all that for gate. And then after that, you diffuse or implant the source and the drain. And what happens is the dopants in the source and drain N+, some of them get under the gate here, into the channel here and into the channel here, which is what is being illustrated here. If you look at this particular picture, what it shows is that this from here to here is my channel length, which is called a drawn channel length. This is the channel length that I've specified, which is 5 micron. But note that this whole region is N+, and part of this dopants, they get into the channel here. They spill over here, they diffuse into the channel here. Because after implantation, you do a anneal step, which is a high temperature step here, and some of them go here. So what you end up getting is a effective channel length, which is not what you specified, but effective channel length is what you specified minus there's an extension of source here, and there's an extension of drain into the channel here. So effective channel lengths are always smaller than the channel length that you actually specify on a mask. For example, if it's 5 micron, you'll get something less here, 4.4 micron here. All right, so let's start with the current voltage characteristics. So the first thing is current is, for our N-channel MOSFET, the current is primarily electron current. The whole current is simply not there or negligible. What we are going to assume is, and as part of a homework problem, you can easily show that when you are above threshold and you're looking at linear region or saturation region, the current can be modeled as primarily drift. Okay, of course there'll be a diffusion component, but as I said, it's primarily drift, which means that the drift component is much larger than the diffusion component here. So Jn, as you know, is Qn, μn, and the electric field. And the electric field, we are talking about current flow in the channel here. So the electric field is the derivative of channel voltage with respect to x here, minus of that. Okay, that's current density. Current is flowing from source to drain here, and you need to integrate to get the overall current. You need to integrate over y and over z. These are the two integrals over y and z. And if you integrate over z, which is perpendicular to the plane, what you will simply get is w. If you integrate over y is, note that vertical. What happens is that n, the electrons that you see here, the maximum is right at the surface, and then as you go deeper, it exponentially decays. And so if you integrate that n, q, n over y, then what you end up getting is total amount of inversion charge. That's the inversion charge per centimeter square. While n, as you know, is electron density is per centimeter cube. So what is Qn? Qn is nothing but Q times n integrated over dy here, from y equal to 0 to deep inside the bulk here, and you don't need to carry out integral very far because the electron density drops exponentially, right? So that's the total inversion charge density here. This is the total charge per centimeter square per unit area, and so the same equation then becomes IDS is W, Qn, mu n, mobility, and of course the field here, dV channel by dx here. All right, so we are talking about, of course, VGS larger than VTN. A channel has been found. And so one of the first assumptions that we are making, we will try and keep track of the assumptions that we keep making in order to derive. So the first assumption that we are making is current is primarily drift. There has to be a diffusion component, but we are saying it's negligible, which is true. It's a good assumption as long as you are above threshold. The moment you go below threshold, you find diffusion component becomes important. If time permits, we will see that. Okay, so this is the expression for current here. Now, we have derived this particular expression for inversion charge density. Inversion charge density is equal to minus Cox, VGS minus VT minus V channel X here. Now, there are several assumptions within this particular expression also. One of the assumptions is, well, you can't see, but one of the assumptions is in Q inversion is that we assumed that the channel is a sheet of charge, which exists right at the interface here. All right, so the assumption is that we have, which we call as charge sheet approximation here. Let me show you with the simulation results what we mean by that. Look at this particular diagram here. This particular diagram okay, so this particular diagram shows you the results from simulation. We have n plus here and n plus here, and what it is doing is plotting the electron density, and it's a contour plot, which means that one particular color denotes the entire region where, for example, the electron density is 10 to the power 19. Then a different, slightly different color shows electron density, which is a little less, maybe 5 times 18, and then 17 and all of that here, right? So if you look at, if I look at electron density, you see that electron density here is of course very high, then it decreases here and then decreases and eventually sort of becomes negligible here. Typical inversion layer thicknesses would be around maybe 30, 40 angstrom, right? So these vary. So 30, 40 angstrom inversion layer thickness is there, but we are neglecting that. We are saying the entire inversion charge is located right at this particular interface. We are assuming that, okay, and which is okay, because if you know if you have a gate somewhere at the top, then the inversion charge and let's say the oxide thickness is for our case is 10 nanometer, right? So 10 nanometer, and this thickness of inversion layer may be 1 nanometer or 2 nanometer here, right? So it makes a difference, but not that much. But then if the oxide thickness becomes smaller, right? If the oxide thickness becomes smaller, then the inversion layer thickness also becomes relatively more important, and you can't really neglect it. Okay, so the point that one is making is that in this simplified model that we are deriving, we are assuming that it's a parallel plate capacitor and the entire inversion charge lies at the interface here. Note that the capacitance is simply C oxide, which assumes that the whole charge is in the form of a sheet lying at y equal to 0. Okay, so that's the assumption, which we call as charge sheet approximation. Even though we know that charge is distributed and inversion layer has a certain thickness. All right. The next thing is there's even more serious assumption behind this. If you recall, the equation that you see here was derived by solving Poisson's equation. By solving Poisson's equation, and we solve Poisson's equation in the y direction. We solve it in the y direction here, and from there del square psi del y square q na by es, and we obtain this particular model here, which is okay in a capacitor. But now note that we have voltages which are of course varying in y direction, and we have applied a drain to source voltage, so voltages are varying in x direction also. So Poisson equation is actually two-dimensional in nature, and I should actually use a Poisson equation which is here, del square psi del x square plus del square psi del y square equal to q na by es, because I have variation in potential, note, along x direction here, and a variation in potential in y direction also. So it's a two-dimensional Poisson equation. while this result was obtained primarily from a one-dimensional solution along y direction of the Poisson's equation. So when will our result be true then? This result will be true if you have del square psi by del x square is much less than del square psi by del y square. If this is, even though we know that psi is varying along x, but if this variation is much smaller than this, then, well, then you can say, well, this equation is approximately true, and therefore this particular model is also true. Okay, so it relies on the fact that the variation of field del square psi by del x square means what? The variation of field in x direction is much smaller than the variation of field in the y direction. All right, this is what we call as a gradual channel approximation. All right, gradual channel approximation, that the field in x is, change in field in x is much smaller than change in field in y, is known as the gradual channel approximation, and we are making that when this is being implicitly assumed when we assume that inversion charge goes like this. Okay. Now this, of course, if you look at this one here, since we know that the voltage along x-axis, typically, let's say whatever is the voltage along x-axis, let's say you have applied 4 or 5 volts, the voltage along y-axis is also around 4 or 5 volts. The gate voltage and the drain voltages, at least in saturation, are same, right? So they're similar. So in that case, if you look at the field in x direction would be something like VDS by L, average field. The field in the y direction is the same, roughly the same voltage divided by T oxide here. So this condition entails that the length by T oxide must be much, much larger than 1. You cannot ensure this condition here, gradual channel approximation, unless the channel length by T oxide is much, much larger than 1. Now, what is much, much larger than 1? As an example, say if you take a 0.5 micron MOSFET, for a 0.5 micron MOSFET, a typical oxide thickness would be around 10 nanometer. And therefore, if you take the ratio is about 50. So, in order to ensure that your MOSFET, this current equation is valid, you have to keep L by T oxide much, much larger than 1. And what is this much, much larger than 1? The order is around 30, 40, 50, around that particular value. If you don't keep that, L by T oxide, then the whole layer is highly two-dimensional in nature. This equation will not be valid. And your equation for currents then, for example, all of you know current in saturation goes as VGS minus VT square. None of that would be valid. Okay, it will not behave like the transistor that you're familiar with if this condition is not true, right? So you will find that when people and a MOSFET behaves, the transistor characteristics are well saturated, and it behaves in the familiar form only if this condition is true. So when people scale the channel length, you want to make the MOSFET smaller in order to pack in more transistors per unit area, also to increase speed. As you scale the channel length, you see that you have to scale the T oxide also. If you don't scale T oxide, your MOSFET will not behave properly. The characteristics will get distorted here. So L by T oxide has to be maintained at a reasonably high value, 30, 40, around that particular value. Okay. The other one is, remember this equation, even if you assume 1D approximation, the more accurate expression was this, where we had Qn equal to minus Cox, VGS minus VT minus V channel plus this gamma term was there, which denotes, this term, if you recall, this term denotes actually depletion charge, and it denotes the variation of depletion charge along the channel. It says that V channel, when you put 0, I have a certain amount of depletion charge. When I put V channel equal to drain, I have certain other depletion charge here. All right. So in general, the amount of depletion charge, if you look at the depletion width, will be high, it will be low here and will be high here as you go towards the drain here. But you are ignoring all of that. When you say that this term is not there, then only you get this simplified expression here. So you're ignoring the variation of depletion charge along the channel. So that's another assumption that you're making here. Okay. From the simulation results, you can see clearly, in this case, what is being plotted is hole density, right? So all this region, one is plotting a contour plot of hole density, and the red one denotes the highest concentration of holes. And then as you go towards lower concentration, the color changes to yellow and then green and then blue. So it becomes very, very small. So the red is where the highest. Now remember, outside the depletion region, I have the highest hole density, right? So in a way, if you look at it, somewhere here is where the depletion width is, because outside then the hole density is significant. So you can see here depletion width is going like this here, high here, less here, and higher here. So depletion width is varying along the channel, but then you are neglecting all of that. When you say that Qn is equal to minus Cox VGS minus VT minus V channel, you are ignoring all of that. So it says you're making another assumption, which is neglect of variation of depletion charge along the channel here. All right. Note that this was in saturation. When you apply a drain voltage equal to 5 volt, that's why you see a significant variation. If I don't apply a large drain voltage, which means the voltage along the channel is uniform, look at that here. The depletion width is the same everywhere. It's only when you apply the drain voltage, which is significant, the depletion width vary here. All right. So with these assumptions, we know that IDS is WQN mu the expression here, and Qn is minus Cox VGS minus VT minus V channel. So all we need to do is substitute it here and collect the terms. So we have IDS W mu and C oxide taken here, VGS minus VT. Only the terms involving V channel are being kept on the right hand side here. Okay. All right. So that's a simple rearrangement. The next thing that we make another assumption is mobility is constant. Note that I've taken it here, and what we are going to do soon is do an integral with respect to dx here and integral with respect to dx here. And mobility, we know that mobility varies with field. As you apply higher and higher field, the mobility decreases, the velocity saturates. Now in this case, in a MOSFET, mobility depends on both the field that you apply between source and drain, which is what we call as Ex, the horizontal field, and mobility is also affected by gate, the vertical field here. So mobility is a function of both the horizontal field and the vertical field, but we are ignoring all of that here. We are saying mobility is a constant. Okay, so that's our assumption number 5. All right, so with that assumption, all that is required now is to integrate this both sides from x equal to 0 to x equal to L here. So let's do that. So assuming mobility to be constant, this whole thing is a constant. So we integrate 0 to L dx, and in this case, at x equal to 0, the voltage is 0, and at x equal to L, the voltage is VDS. Everything is being measured with respect to source, so VDS here, and so we integrate from 0 to VDS. So it's a simple integral. Here you'll get L, and here you'll get VDS minus VDS squared by 2. So you end up getting your familiar expression for current, which is IDS is W by L mu Cox, VGS minus VT, VDS minus VDS squared by 2. Okay. Now this equation, remember there are many assumptions. Of course, I'm assuming that there is inversion charge throughout, because we have taken this expression for inversion charge, VGS minus VT minus V channel, this one here. And obviously, I can only apply this particular equation if the inversion charge is greater than or equal to 0 here. So it says the inversion charge will be minimum close to the drain, and that minimum value must be greater than 0, which means that VGS minus VT minus VDS must be greater than 0. Or it says VDS must be greater than VDSAT, which is VGS minus VT. You can only apply this particular equation as long as VDS is less than VGS minus VT, right? Because after that, the inversion charge is becoming, negative. Negative inversion charge doesn't have any meaning. It implies there's an accumulation of holes which can't happen here. And this equation is valid only under this condition. So that's the limit of validity of this particular equation. VDS less than VGS minus VT. All right, so these are the assumptions that you see here. The simple familiar expression that you know, W by L mu Cox VGS minus VT, VDS minus VDS square over 2. The assumptions that are being made is current is purely drift, charge sheet approximation, gradual channel approximation, negligible variation of depletion charge along the channel, constant mobility, and I've added one more, which is negligible source and drain resistance. Because note that we've been only focusing our attention on the channel. From the channel, the current has to finally come out of this particular terminal. And as it comes out, this N plus layer, even though it's heavily doped, it has a certain amount of resistance, which we call it as the drain resistance here. Similarly, for electrons to again reach the channel here, they have to flow through N plus, and so there's a certain amount of resistance called source resistance here. And therefore, when I apply a voltage VDS, the entire voltage doesn't appear across the channel. Some gets dropped here, some gets dropped here. Similarly, when you talk about VGS, the voltage between here and here, the entire voltage doesn't appear across the gate here. Some voltage gets dropped across the source here. So these, when I'm writing an equation like this here, I'm implicitly assuming that the drops here and the drops here are negligible, which means that the source and drain resistance are negligible, right? So a lot of, when you're doing processing, a lot of effort goes in keeping these resistances small. If you don't do that, then your characteristics gets dominated by RS and RD and not by the channel, right? Which is what you really desire. The transistor, the current should be determined by the channel characteristics. So that's another assumption that we have implicitly made when we have written simply VGS and VDS and ignored this RS and RD. Okay, so let's take this particular equation and let's look at it under certain limiting conditions here. One of them, okay, so again, the same example that we'll use for same doping, oxide thickness that you see here, all of that is given here. For these Na and T oxide and phi m, if I calculate, I obtain a threshold voltage of 0.805 for this particular transistor here. All right. Now, if I look at this particular equation here, IDS, and I look at my current for very small values of VDS, right? Very small values of VDS here, then we know that IDS, whether in either case, whether it's very small or large, you know that current in this case goes as VGS minus VT. So current is directly proportional to the gate to source voltage here. So in this case, I've done the simulation and I'm plotting from the simulation IDS versus VGS. And we get a graph like this here. Does it make sense? This graph? IDS versus VGS here. Note how much voltage have I applied? 0.1, very low voltage. So which means my transistor is biased in linear region, in the ohmic region here. And IDS goes as VGS in this particular manner here, right? And now this is a very useful characteristics because, we've been talking about threshold voltage. And we have a model for it. But then in order to check my model, I need to measure it also. So for example, a plot like this is very useful. IDS versus VGS. If you do it for very small VDS, what you can do is you can take this particular plot, fit a straight line, and then you can measure the intercept and you can measure the slope. And if you look at this particular equation that we just derived here, W by L mu Cox VGS minus VT, VDS minus VDS square over 2, this can be written in this form as well. Take VDS out, it can be written like this here. So if you look at this intercept here, where is, from the intercept, can I determine VT? From the intercept of this graph? So here, note that intercept is given. And from this intercept, what will we obtain? VT plus 0.5 VDS. And that turns out to be, if I take this particular intercept, it turns out to be 0.86 here. And therefore, VT turns out to be 0.81. My calculated value was 0.805. Right? So that's how you check. For example, you have a model and then you make a device and then you plot IDS versus VGS in linear region. Take the fit a straight line, take the intercept, and from the intercept you end up getting the threshold voltage. Now, the other thing is slope. The slope is going to give us what? W by L, mu Cox, and VDS, right? And now note that W by L is known, C oxide is known, oxide thickness is known, VDS we have applied as 100 millivolt, and therefore what do you end up getting? The mobility. So that's a way of measuring what is the mobility of carriers in the channel. So two very important parameters, threshold voltage and mobility, you can get by this very simple plot, IDS versus VGS in linear region and from the slope. In this case, the mobility that we extract from here is 514. The mobility that was put in simulation was 500. But then note that we have many assumptions that I have listed there. And so 514 versus 500 is fine. Okay, so it's not that much off here. All right, so this was in a linear region. We know now that the current IDS varies linearly with VDS. This term is negligible compared to VGS minus VT. So your MOSFET behaves like a resistor whose value you can control by using VGS minus VT. Let's look at the saturation. Now, note that what happens is if you look at, these are things that you're familiar with. This is the expression that we have derived. And this is based on an inversion charge. And if I look at inversion charge at the drain end, then we put minus Cox, VGS minus VT minus VDS. So as I keep on increasing VDS, what is happening is that the inversion charge at the drain end keeps on reducing. While at the source end, what do we have? Cox, VGS minus VT. At the source end, the inversion charge is constant. At the drain end, the inversion charge decreases here. Now we know that IDS is WQN mu times field. So now if your inversion charge at the drain is decreasing, then what happens is the field at the drain end starts building up, right? Because note that according to this expression, as you increase VDS, your current is increasing. Current is increasing. But then if I go to the drain side and I look at the drain side, the charge is actually decreasing. If charge is decreasing, then this term that you see here, this has to rapidly increase to compensate not only for the decreasing charge, but to also allow the current to increase here. So what you note here is that the field next to the drain builds up very rapidly, builds up to high values. But then note that this term has an upper limit. Mobility times field cannot go above the saturation velocity. So in a silicon device, I have a saturation velocity close to say 10 to the power 7 centimeter per second. So this has a limit. Beyond a certain stage, I can't keep on increasing this. And so eventually the velocity saturates, and that happens. Note that it will happen at fields which are fairly large. You need fields of the order of 10 kilovolt per centimeter to cause this velocity to saturate. So fields become very high. And when do the fields become high? When the inversion charge becomes fairly low. So what is happening is as you approach a region where the inversion charge next to the drain is getting zero, which means the channel is getting pinched off. The field is building up and the velocity is saturating and the current also saturates here. Okay. So note, this is just illustrating, for example, if I look at my simulation results again, this is VGS equal to 3 and very low drain voltage here. This is showing electron concentration. And this color denotes the highest. I don't think you can see the color very well. All the shades are not coming on this one here. So you have almost like uniform electron concentration here. But now look at this particular picture. Can you see anything at all? Nothing. Right. So there are actually, maybe you can see it later on in the slides. It shows, that the electron density is high here and then electron density is decreasing. And eventually, electron density becoming very, very small here. All right. So using different shades, you can see it later on. This you can see. So note that what is happening, electric field. Look at that electric field in the channel. Not very high. But then as you start approaching the drain side, because the carrier density is the channel has been pitched off. Look at the electric field, how rapidly it is changing close to the drain side here. Right. So what is happening is, if you apply a voltage which we call as the saturation voltage, then the channel here is getting pinched off. The channel is getting pinched off. So for our example, if I have gate voltage of 3 and my threshold voltage we said is 0.8. So if I apply 2.2 volt here, then my channel will be pinched off close to the drain side. Right. And channel will be pinched off and we are getting a high resistance region here. Right next to the drain. The fields are very high. The resistance is very high. Okay. And the current then, the moment this happens, the current then becomes almost constant here. And the reason, a very simple qualitative explanation of why current is constant. Well, if you take linear region, you can think of your channel as made up of small bits of resistances here. And if you apply and increase the voltage, the current of course increases throughout the channel here. But then the moment you get close to saturation or close to pinch off, what happens is the resistance in the channel is, is reasonably small. But then as you get close to the drain, you get resistance which is very large, very small inversion charge density. So now if you apply an incremental voltage here, you know that everything will get dropped here, hardly anything will get dropped here. Right? And if nothing gets dropped, very little gets dropped across this region here, which means that the current that flows here is very, very small here. So basically, pinch off is occurring, a high field region is developing close to the drain. That's like a high resistance region. And all the extra voltage that you apply gets dropped in those particular high field region here. The rest of the channel remains practically untouched. Nothing really happens in the rest of the channel here. Okay. Look at this particular picture of potential. We have 5 volts supplied. Look at potential here. And at the moment you come close to the drain side, look at how the potential is rising. Rising from about 2 to 2.2 to about 5 here in a very, very short distance. So this is denoting all the, potential, excess potential over the saturation voltage is all getting dropped here very close to the drain edge. Okay. Now this is, so if I take my current equation here and note that this current equation, and if I plot it, the current equation is this black line here. It goes here. And at this particular point, what has happened is my channel has become pinched off. And after this, I cannot apply this equation anymore, right? If you apply it, it denotes a falling current here, which is the equation has validity only at this particular point here. Okay. After that, we said the moment channel gets pinched off, the current saturates and you get this particular value. Okay. So this is what I would expect from our simple model here. Now, from simulation, we are getting this one here, the blue line here. The simulation is predicting a current which is smaller than the saturation current that you're familiar with. And we had discussed this in the last lecture. The reason is that the inversion, we have neglected the variation of depletion charge. If you recall, we were discussing that if you neglect the variation of depletion charge, what you're doing is you're overestimating the amount of inversion charge in the channel and you're overestimating the current in the channel here. So that's the consequence of one of our assumptions, that the current that this model predicts is actually larger than the actual current here. All right. And the difference is significant. It's not something that you can, so current here probably is around 6.5 or so, and current here probably is 8, right? So it's not negligible, but that's coming because of, so we can take this model and make it more accurate, but as a first, first iteration, the simplest model, we take it as W by L mu and C ox VGS minus VT square. Now beyond, so this is where the channel just gets pinched off. This is at the saturation voltage here. If and note that, as we have been saying, that once you go beyond pinch off, the drain doesn't have much influence. All that happens is the pinch off point that you see here moves a little bit to the left of this particular point here. The rest of the channel actually remains the same, and current then it has saturated. The current now no longer obeys the drain voltage here. You can change the drain voltage here, the current doesn't change, and therefore you have very high output resistance. And from your earlier background, you know that the drain becomes insensitive to the drain to source voltage here. But the drain current remains sensitive to gate. If I change the gate voltage, it will change all this charge here. So the current remains sensitive to gate voltage here, but it's no longer sensitive to drain. Drain has been sort of, because of this high field region here, all this channel is sort of disconnected from the drain. All the voltage that you apply, extra voltage that you apply, gets dropped here. Nothing really happens here. So it's sort of channel getting disconnected from the drain. And therefore, the current does not respond to the drain voltage. So this term becomes very small, which means that the resistance becomes very large. And this, of course, remains very high. So this is the condition for amplification, voltage amplification. Transconductance much larger than output conductance. So you start getting that the moment you create pinch off or you enter saturation region. Anything extra that you apply, as we have said, 2.2 was where the pinch off occurs. Anything extra that you apply, say if you apply 5 volt here, the pinch off point, as we said, moves towards the left here. So the voltage at this particular point is 2.2. The voltage here is 5. So 5 minus 2.2 is what gets dropped here in the small region here, right? And therefore, what we get is what we know, call it as the channel end modulation. If you look at this picture, this picture here, the channel is all the way from here to here, and the length is L, right? Now, the moment I've applied a voltage larger than the saturation voltage, my effective channel is from here to here. And this is a high field region. Whatever electrons enter these high field region, they're rapidly collected. So this is not a bottleneck. This is the effective channel length here. So channel length has become a little smaller, L dash, and this is the high field region here, delta L. So your current expression now remains the same, except that you don't take L, you take this as the channel length here, which is L dash. All right. And as we apply higher and higher voltage here, this point shifts further and further to the left. And you know that L dash will become a little bit smaller and the current increases here. Right. So once you go beyond the saturation point, our model for current then becomes W by 2 L minus delta L, which is L dash here, mu and C ox VGS minus VT square. Now we can, because this delta L is very small, one can rearrange this one. One can take L out. You'll get 1 minus delta L by L, and you can take it to the numerator. It becomes 1 plus delta L by L. All right, so we can easily do that once the change in length here is small. The other thing that you can do here, I'm going to build a very, very simple model, the simplest possible model for delta L here. So delta L is, the voltage at this end is VD sat, the voltage at this end is VDS. Right, so the drop in this particular region is VDS minus VD sat. And note that the I'm going to have, it's a very small region. The field is going to vary in this particular region, but because it's very small, as a first order approximation, assume that there is some average field in that particular region here. All right. As I said, of course, the field is going to vary, but it's a very small region. So the simplest that you could say is, well, the field is some average, and therefore this delta L that you see here will be equal to the voltage dropped, which is VDS minus VD sat, divided by the field here, average field here. So that's a simple model for delta L, and we get this particular expression. W by 2L mu n C ox VGS minus VT square 1 plus VDS minus VD sat divided by average field. We don't know what the average field is, but we are saying it has some value, multiplied by L. Well, if that is there, then one could take this F average into L and note that it's a field into L. So it has units of voltage, and one can define this as a new quantity called lambda. And therefore, we have a parameter called lambda as a channel and modulation parameter, which tells you that the drain current in saturation increases slightly because my effective channel and becomes smaller here, and characterized by this particular parameter here. So for us, lambda is 1 over F average into L. Now, as I said, it's a very simple model. We don't know the value of F average. It depends on many other factors. It depends on doping, depends on junction depth, and a lot. But one of the things that this particular model tells you is lambda is inversely proportional to L. That's a very important point. That lambda channel length modulation parameter goes as L is going to play a very significant role. And let me show you. So the longer the L, the smaller the lambda. And this is what you require from a transistor. Small lambda means high output resistance here. So let me show you through some simulation results how lambda changes with L. So for the example that we are discussing, this is IDS versus VDS. Looks very well saturated. You can't really see that the current is increasing with L, but if you zoom in, this is how you find that the current is indeed increasing. And the increase is described by this expression. W by 2L mu n C ox VGS minus VT square 1 plus lambda VDS minus VD sat. So the current, if you zoom in, current is increasing. Now what I can do is again fit a straight line, take an intercept and a slope. The slope, slope is nothing but derivative, and I can express it as W by 2L mu n C ox VGS minus VT square into lambda, the simple derivative. Normally lambda is small, so one could, this whole term that you see here, the first part, we could approximately write it as the current ID sat times lambda here. So once I measure the slope is given here. The current is, note that current is changing, but you can take an average current here over this region and then calculate lambda. Turns out to be 2.7 into 10 power minus 3. Okay, fairly small value of lambda. Why? Because the channel length is fairly large, 5 micron. 5 micron transistor, lambda is very, very small value. Suppose I did the same thing now with 1 micron transistor. Exactly same, simulate a 1 micron transistor. Do that, lambda turns out to be 3.3 into 10 power minus 2. Note the difference. 5 micron transistor, lambda is here, 10 power minus 3. 1 micron transistor, how much has it fallen? 1 order. Fallen means risen. Lambda has increased by 1 order of magnitude as you reduce the channel length. So that's the problem that you face. When you reduce the channel length, lambda starts increasing, your output resistance starts falling, which then makes it more and more difficult to design analog circuits where you require large output resistance here. Now, according to our simple expression, if F average were constant, if you reduce channel length by a factor of 5, your lambda should have increased by a factor of 5. Well, it does increase, but more than that. It increases by a factor of 10. All right. So, but this does capture a very important point that channel length modulation becomes more important as you go to a smaller channel length. And lambda is a challenge to obtain small values of lambda at small values of channel length here. All right. So that's so we have seen now transistor characteristics in linear as well as saturation region. A very important point is subthreshold. So I showed you this characteristics and IDS versus VGS for a transistor bias at 0.1 volt in linear region. It shows here. But this particular picture is misleading because it gives an impression that around threshold voltage or below current is 0. The current is not actually 0. If you plot it on a log linear axis here, this is what you obtain. The same graph you obtain here. So what you find is that the current, this is my threshold point, below threshold, which means all this is the subthreshold region, the current is actually dropping exponentially. Current is changing exponentially because this is a straight line in a log linear plot. So this is an exponential here, and the current is changing exponentially here, dropping rapidly. Now this region is of importance because, you know, when I'm taking my device and I'm biasing it below threshold, maybe I'm applying 0 volt here, and I want current to be negligible, right? The current here to be negligible here. Off-state current has to be small, but then think about the following. If this line here has a fixed slope, and if you reduce the threshold voltage, what would it imply? Let's say this line has a fixed slope. You design a transistor with higher VT, right? Higher VT. Let's say VT is 1.5. What would the off-state current be then? This line has a fixed slope, and you shift the whole characteristics to the right. What would it imply about the current at 0 bias? Low. Current would be even lower. But then if you shift VT towards the left, and the slope is fixed, the current is going to rise, right? Current is going to rise. Now, why do you want VT to be low? Well, for a number of mobile applications and all that, you know that you want to operate at 1.5 volt, right? Or even 1 volt. Now, if you have a VT of 0.8 and your supply voltage is 1 volt, how much, you have over VT, you have only 0.2 volts. You won't get enough current. So as you're reducing the supply voltage, you have to shift towards lower VT. You have to reduce VT. But note, as I said, if this slope is constant, which we will see in a minute, that as you shift VT towards this, what would happen? Your off-state current goes up. This is a major problem in current technology. You've gone towards very short channel length transistors. You want to operate at very low supply voltage, and therefore you want to make threshold voltage small. And as you make threshold voltage small, the off-state current becomes very high. Subthreshold leakage here, the off-state current here. Here, don't get confused by this value here. This is 10 power minus 15, is 5 micron transistor, and my width of the transistor I've taken 1 micron, right? Suppose I have 50 micron. So the current would become 50 femtoamperes. Fine, it's very small, but then that's 5 micron, right? So now start decreasing VT. And then you'll start seeing the off-state leakage becoming more and more important. So it's a major headache right now in current technologies, this off-state leakage here. And this brings us to the importance of that this slope is very important. Because VT is one parameter, and how large is your off-state current would depend on what this slope is. If this slope is very high, what would you expect for a given VT? Off-state current would be smaller. If the slope is high, if the slope is low, it's going like this here, the offset leakage becomes very high. So you know that the slope that I'm talking about of this characteristic is a major, very, very important parameter here. Okay. All right. So we're talking about subthreshold here. And so slope. So what we want to do is calculate what that slope is. Okay. How much is this particular slope here? So can we go 15, 20 more minutes today? Is it okay with everybody? 15 more minutes after the bell? We'll do the subthreshold and then we'll stop there. Okay. All right. So the first thing to understand is in this subthreshold, why is the current changing exponentially? Here we know that the current increases with gate to source voltage as linearly in linear region and quadratically in saturation region. Right. So here we know the behavior. Why is it changing exponentially here? All right. So let's try and understand that first. Okay. So this was the expression that we had derived for our three-terminal MOS structure here. How gate to body voltage is related to surface potential, is related to depletion charge, related to inversion charge. All right, this whole expression here. Now, when you are below threshold, note that what is the electron density here? Less than the background doping, less than Na. So inversion charge is there, but compared to, it's very important, compared to these terms is negligible. Because remember, what is the depletion charge due to? Depletion charge is here, and where does it come from? Background doping. What is the doping order? Na. And if we say that the electron density at the surface is less than Na, electron density everywhere will be much smaller than Na. And therefore, this inversion charge compared to this term is negligible. So in my expression, I'm not saying inversion charge is 0. I'm neglecting inversion charge with respect to this. Okay. So this is a more accurate expression. My surface potential is now no longer 2 phi f plus VSB and all that. I have some surface potential, which we call it surface potential measured with respect to bulk. And similarly here, surface potential measured with respect to bulk. So now note that what is happening as you are changing the gate, body is fixed, let's say source is fixed. As you're changing the gate voltage, what you're doing is you're changing the surface potential. All right. Let me rewrite it in a little bit. So VGB that you see here, we can write it as VG minus VB, which is from definition. In addition to that, I subtract VS on left hand side, source voltage, and VS from the right hand side also. And all that it is trying to do, and then I can cancel out VB here and cancel out VB here. It allows us to write everything in terms of gate to body, everything in terms of VGS. VGS is V flat band, psi S. Now is surface potential measured with respect to source. And this is also measured with respect to source. And this is the body to source voltage. All right. So this is same equation, but little with a different reference here. The electron density at the surface, we had written down earlier, Ni square over Na, Fermi level at the surface minus Fermi level in the bulk, Kt exponent Q psi Sd by Kt. With the same changes here, electron density can be written as Ni square over Na, exponent Q psi S by Kt. Electron density changes exponential with surface potential, which we know. So now look at this one. As you change, focus on this one. As you change the gate voltage, what happens to surface potential? Increases. Or if you decrease gate to source voltage, surface potential decreases. As this decreases, what happens to electron density? Decreases exponentially. So now, what would you think is the dependence of N on Vg, on gate voltage? How will it change with gate voltage? N changes exponentially with psi S. Psi S, look at the relationship between psi S and Vg. If this term were dominant, it's linear, but then I have a square root also. So psi S would be somewhere between linear and a square root kind of in between that kind of a variation, right? With respect to Vg. So what would be, in general, the variation of Ns with Vg? It would be exponential also, right? So can we say now, if we look at this one here, look at these two terms here. Psi S is maybe sublinearly related to VGS, because this is square root and this is linear, sublinearly related to VGS. Ns is directly proportional to psi S. Can I write Q inversion would be exponentially related to VGS with some factor? Q inversion charge would change exponentially with VGS. Okay? Which will then imply if inversion charge changes, then it would imply your drain to source current would change exponentially with VGS. Okay? So this is what we are saying, why current varies exponentially in the subthreshold. Then why does it, if inversion charge, why is it then inversion charge changes linearly in above threshold. Above threshold, what is happening? This term becomes relatively fixed. This term fixed. And then only this one is increasing. And the Q inversion increases linearly with VGB. But below threshold, this is negligible here. And the major, any time you change VG, you're changing the surface potential here. You're changing the surface potential here. And electron density changes exponentially with surface potential. And therefore, it changes exponentially with gate voltage. So that's the reason why you're finding that the current changes exponentially. The reason is electron density changes exponentially. All right, so let's look at the slope here. We define a slope d log id because it's log divided by dvg. And we call this parameter s, this is 1 over s here. And this parameter s is what we call as subthreshold slope. It's a slope s in the subthreshold region, and we call it subthreshold slope. Now, if you look at it, what is the significance here? S I'm writing as 1 over s is d log id by dvg. I can also write it as same thing. This is in the derivative form. This is if I change gate voltage by an amount delta Vg, my current would change by ID2 by ID1. Right? Okay, so I'm writing now S instead of S inverse. So S will be equal to change in gate voltage, which is delta Vg, by change in this term, which is log ID2 by ID1. So what is S? I mean, how should we physically understand S? S is see whether it makes sense. Is the change in gate voltage required for 1 order of magnitude change in current? That's how you should think of S, right? ID2 by ID1, if it's 1 order, 10, log of 10 is 1, and therefore S is nothing but the change in voltage. So is the change in gate voltage required to cause current to change by 1 order of magnitude? All right. So if you want to go from, let's say, this current and you want to change by 5 orders of magnitude, how much gate voltage you have to apply? 5 multiplied by S. So S denotes that. All right. So the amount of gate voltage required for change in the current here. And obviously, we require S to be as low as possible. S to be as low as possible. We want this slope to be high. This d log id by dvg has to be high, as we just saw, in order to minimize the off-state current. And therefore, S we want to be as small as possible. Okay, S delta Vg by log id. But one can show that the minimum value of S that you can get from a MOS transistor is minimum value, absolute minimum value is 60 millivolt per decade. For 1 decade change, the minimum that you can get is 60 millivolt. All right, that's the best that you can get. That's what I said. The slope is relatively fixed. You can't alter much. Okay, the actual value of slope, we'll just derive it in a minute, what this value is. So 60 is absolutely minimum. Typical values are 85 or 90, around that value. So this is like 90 millivolt per decade. And relatively constant, doesn't change that much. And therefore, as I said, if you change Vt, it would affect your off-state current. Okay, so S is delta Vg by log ID2 by ID1. We call this the off-state current at zero bias. I can write as S equal to, so I go from Vt. What is the delta Vg? I go from Vt, is that right? So S is equal to Vt here and 0 here. So S is equal to Vt, delta Vg is Vt. Current log is the current at threshold, I0, versus the current at off here. Right? So S, Vt by S denotes how small is your off-state leakage compared to current at the threshold here. So what you're looking for from a MOSFET is Vt by S to be a large quantity. Vt by S to be a large quantity here. Now, one way of doing that is make Vt large, but we can't do that for a low voltage operation. So you have to keep Vt small. And the other way to keep this ratio large is make S large, or subthreshold slope is small. Okay. So off-state current increases exponentially with reduction in threshold voltage here. All right. Last, what we'll do is quickly derive this particular expression here. Okay. So look at this. It's a two-step derivation here. What we are saying is IDS goes exponentially with VGS. How? Well, N goes exponentially with psi S, which causes Q inversion to go exponentially with VGS, which causes ID to go exponentially with VGS. All right, so that's why we get exponential here. Now, with this in mind, can I say IDS goes exponentially with psi s? What is causing IDS to change is change in electron density, and electron density changes exponentially with psi s. So what I'm saying is IDS is changing exponentially with psi s, right? So now d log IDS by dVGS would be d log, all these extra terms it doesn't bother, exponent q psi s by kT by dVGS. All right. So what one is saying is current, yes, it goes exponentially with VGS, but why? Because current actually goes exponentially with psi s. So that's one is writing here. So if you take this, then this comes out to be Q 2.3 kT d psi s by dVGS. Derivative of surface potential with respect to VGS. We have this expression here. We can take its derivative. This whole thing is depletion charge. If you take its derivative, you get 1, you get 0, you get d psi s by dVGS. This whole thing is depletion charge. So if you take its derivative with respect to psi s, you get depletion capacitance by Cox, d psi by ds here. And so you get expression for d psi s by dVGS from here, and you plug it here, and you get an expression for subthreshold slope, which is 2.3 kT by Q, 1 plus C dep by C oxide. Depletion capacitance divided by oxide capacitance. And so this is the value, and you can see here, if you change anything, the best that you could do is make this particular term equal to 0. Make this term equal to 0, and the best that you can get is 2.3 kT by Q, which is nothing but 60, close to 60 millivolt here. So that's the lowest subthreshold slope that you can get here, which is 60 millivolt per decade, right? And so for the MOSFET that we are talking about, we get a subthreshold slope of 89.5 millivolt per decade. From a simple formula, 1 plus C dep by C oxide, we get 94 millivolt per decade, right? So that's the subthreshold slope, and this is the from more accurate simulation-based analysis, you get this value here, right? So the important point is that this characteristics has a slope here, and subthreshold slope is important because it decides for us how much is the offstate leakage. For a given VT here, it decides what is the offstate leakage here, and therefore we are looking for subthreshold slopes which is as small as possible here, right? And there's a lot of research right now which is taking place. As I said, the threshold voltage people have reduced to very small value, for very low voltage operation. And this is a major headache for everybody. That subthreshold slope, the best that you can get is 2.3 kT by Q. It's a major headache because the slope is remaining constant. You want to reduce VT to smaller value, and you end up getting large offset leakage. So the major headache is how can I violate this? Can I get subthreshold slope which is lower than this? So people are thinking of different structures. You'll hear if you maybe in later courses tunnel FETs and all kinds of different structures. The idea is to break this particular limit, 2.3 kT by Q. One, of course, very simple way is you go to low temperature, right? Go to lower temperature, and then you get. Don't shake your heads. kT by Q. That's a viable option, right? You take your MOS and you operate it at 77 Kelvin. Liquid nitrogen is 77 Kelvin, and you operate it there. For some application, you have very high performance supercomputers and all that, you could do that, right? So get rid of leakage and use that particular technique. All right, so let me stop here and